Richard James Mathematics Resources will continue the presentation of Grade 4 Practice Paper 5 with Part B. And it has now become a chorus that videos A, B, and C contain the solution of 12 problems. So we will continue with the second phase of 12 problems in Practice Paper 5. First 12, then this is the second. This one will begin at problem number 13 and end at problem number 24. What is the value of the 8 in 180,260? What is the value of the 8? Can Jerry tell me the value of the 8? Okay, Jerry took a few seconds to analyze it, but came up with 80,000. Let's see if that is correct. The value of the 8 is dependent on its place value. Let us write the number down and include all of the place values. So we will write down 180,260, and we are including all of the place values. The smallest place value, which is the rightmost, is first, and we increase in size towards the left. So we begin at the rightmost digit, which is the ones digit, then tens, hundreds, thousands, tens of thousands, hundreds of thousands. The place value of the 8 is tens of thousands. Tens of thousands. The value of the 8 is therefore 80,000, and that is represented by option
C.
80,000.
Option D.
Right, that is represented by option D, 80,000. When dealing with numbers, the suffix t, like 60, is related to the tens digit. The phrase 8 tens of thousands is read 80,000. Because the word 8 ends with a t, the t is dropped or discarded before the suffix t is added. So 5 tens, that's 50. 7 tens,
70.
that's 70. So the suffix t is related to the tens digit. But because we have 8 that ends with a t already, we eliminate the t and then add ty. So 80. 8 tens of thousands. 80 thousands. Notice that 8 is in the tens of thousands. So 8 tens of thousands. 80 thousands. Roy bought a toy car for $350. Jerry is so fast with these problems. He received $150 change. Which note did he spend?
200. 500.
Right. So he spent $500. And that is not a difficult problem. Why? Let's see. Every shopper knows this basic principle. The change and the price must add to give the amount of money that you had. So the change that you received and the price of the article that you purchased, those must add to give the amount of money that you had before. So that is your change. That is the price. When you add those, you will get the amount of money that you had before. Begin by adding the ones digits. 0 plus 0,
0.
0. And 5 plus 5,
10.
what do? Place 0 at the present place value and carry 1 to the column of greater significance. So 0 will take its rightful place. The 1, being a tens digit, is carried to the left, where we find those digits that are of greater significance. And the 1 to the left, to the immediate left, is always 10 times the present place value. At the hundredth digit, what do we get?
4, 5.
We get
5.
5. So 1 plus 1 plus 3, and that is equal to 5. So place the 5 in the hundreds column. And what do we get for our answer?
500.
Right. And we need to include the dollar sign. We are dealing in dollars. It does not have to be in our calculation, but it has to be in our answer. The correct answer is option B. We may take a look at the problem in the reverse, because we need to know how much change we will receive from a particular note if a certain amount of money is spent. So purchasing for a particular amount, spending a particular amount, and the change received may be viewed in many different ways. And those three components may be used for a variety of reasons. Now, in this particular case, we may take a look at the problem in the reverse, because we need to know how much change we will receive from a particular note if a certain amount of money is spent. So that's another problem that we might be able to solve. We have a certain amount of money that we have shown to be $500, and let us say that we do not know what the change should be. How can we tell? If we spend $350, then the amount of money will be reduced. $350 is gone and has to be taken away from $500. So if we had the amount of money and we had the cost of the car, then we may be able to determine the amount of change that we should receive. So we are not taking this problem and just solve, get the $500 note, and then we are off and running. We are taking a look at the problem from different angles, different perspectives, because when you go to shop, there might be a variety of problems that you need to address in order that when you go out, you know how much money you are spending, how much change you are to receive, or if the cashier made an error, or you know ahead of time how much money you need to have. So we are taking a look at this from different perspectives. The answer that we get will be the amount of money that we did not spend, which is the change. So we take the amount of money that we have, we reduce the price of the article, and what we receive will be our change, which is the amount of money that we did not spend. The answer will therefore be our change. We will begin our subtraction as usual at the rightmost digit, the one with the smallest place value. That's fast. We cannot take 5 from 0, so we go to the greater place value and rename the 5. And do not forget that our present place value is this one, correct?
Yes.
This is the one that we are subtracting in. What do? Rename the 5 to 4. And remember that the place value to the left is always 10 times the present place value. Therefore, what we have in these tens right here, we are taking from the hundreds. Therefore, we have 10 tens that will be placed there. So the one taken from the 5 is 10 times the digit of less significance. The 100 will be 10 tens. 10 will be added to the 0 that is already there. So 10 plus 0 is equal to 0. The digit is written in that way in order that it might be accommodated. So we know that 1 we are taking from the hundredths column. So the 1 from here will be 10 tens. So we are adding 10 to the value that we have here, which is 0. So 10 plus 0 is equal to 10. So we put the 1 right there. We could not just write a full scale 10. We could not write a full scale 10. Therefore, we write it in a reduced form. So the 1 is reduced and placed right there so that it may be suitably accommodated. So 10 minus 5 is equal to 5, and 4 minus 3 is equal to 1. When dealing in currency, monetary symbols must be included. When we subtract the amount spent from the money that you had, the result is the change that you got. We may also check for a cashier error, or just to confirm the price of an article if we spend an amount of money that we know to be $500 and our change is $150. So this problem may be turned around in many different ways. The problem was given to us for us to find the amount of money that was spent. Also, we rearrange the problem to determine the amount of change that we should receive. And now we received our change and we are checking for a cashier error or the price of the article if we did not know it. So this problem may be turned around in many different ways because shopping comes with many different problems, many different pitfalls, many things that we need to calculate in order that in this day and age we are sure of what we are doing when we are spending our hard-earned cash. The money that we had is the total amount, which is that $500. The change is $150. The price of the article is the other portion. We therefore need to subtract the change from the $500 and the answer is sure to be the price of the article. If the answer is equal to what the price was claimed to be, then we are okay. If the answer is different, then we revisit the transaction. And this is the day and age for spending money. Money over internet, internet banking, wired money or remittances, digital currency, hand-to-hand cash, credit card, debit card, online sale, all different ways that money is running around in this day and age, and we need to be able to make these basic calculations in order that we may do our reconciliation correctly. So on this occasion, we will begin our subtraction as usual at the rightmost digit. We have our change. We have the original amount. Let's see what the article cost. If when we subtract and we look at the price tag on the article, if that is different, then we know that we have a serious problem. So we may just do that as a confirmation, or we may do that in order just to know. We cannot take 5 from 0, so we go to the greater place value and rename the 5. We have done that before. The 1 taken from 5 is 10 times the digit of less significance. The 100 will be 10 tens. 10 will be added to the 0 that is already there, and we'll get 10 plus 0 is equal to 10. The digit is written in that way in order that it may be accommodated. So we write it in a small fashion so that we can still see that we have a 10 there, but it does not get in the way of the other digits that are there already. So we will say 10 minus 5 is 5, and 4 minus 1 is 3. When dealing in currency, monetary symbols may be included. So we need to include our dollar sign. Do you think that we have all of the problems involved? Or we have exhausted this problem as yet?
No.
Alright, let's see. The price can be confirmed or discovered by subtracting the change from the original amount of money. So we may confirm that the price is correct, or we may check to see what the price is by subtracting the change from the original amount of money. No, the problem was not exhausted. We may reason by making use of our common sense and identify the correct option without much calculation. Without making much calculation, we may do what? Reason by making use of our common sense and identify the correct option. How so? The amount of money in options C and D cannot be right because they are both less than the change and also less than the amount of money spent. So we got a change of 150. Can it be that we spent $100?
No.
You cannot spend $100 and get a change of $150. That's just not practical. It's not possible. And the same applies to option D. Those values are less than the amount of money spent and less than the article in price. Less in price than the article that we purchased. Those cannot possibly be the correct answer. If we consider the relative sizes of the figures, $1,000 would immediately appear to be too large. That is really making an estimation, but estimating is very good in mathematics. Now, if we are just dealing with $350 and $150, is it possible that that can jump all the way to $1,000?
No.
Right. Therefore, the answer cannot be $1,000. So, $1,000 not possible. We are only left with option B, so option B is correct. As a matter of fact, it is correct, and we did not do any calculation. In mathematics, the ability to estimate is so important that in GSAT and in the CXC CSEC examinations, mathematics examinations, there are actual problems that require that you do it. So estimation, you might find the need to estimate in GSAT, because I have seen problems in GSAT that requires that you estimate. And CSEC, we have seen problems that require that you estimate. And although it is not full-fledged estimation, there's a problem like that sometimes on the grade 4 numeracy examination. So making an estimation is not a very bad thing. It is by good judgment that you make your estimation. And as a matter of fact, turns out that it gave the correct answer, which shows $2,540.60. Which shows $2,540.60. And Jerry?
Option B.
Option B. Jerry is saying that it is option B. It surely looks like option B to me, but let us take a closer look at it. The number begins in the thousands. We need to have a group of digits for the thousands. So the number started where? Thousands. Right. And we need to have a group of digits for thousands. And another group for the digits that are to follow. So if we do that, what do we notice? We have a group of digits for the thousands, and then after the thousand we must have what? The hundred, tens, and ones. So we must have for the thousands, and we must have for the hundreds, tens, and ones. In the thousands group, there are no hundreds and no
Ones.
Let's go again. No hundreds and no.
Tens.
Right, we only have 2,000. 2,000. So there we do not have any hundred of thousands, and we do not have any tens of thousands. Only 2 ones. The other place values will be zeros. What will come after? $540. 540. 500s and 4 tens. Remember that those numbers that end with TY, like 40, 50, 60, they are the tens. Correct?
Yes.
Right. So we have 500s and 4 tens. $540. 504 tens. There is no one. And then we have 60 cents. The leading zeros may be discarded as they contribute no value to the number. We will also include the dollar sign. Do not forget that we are dealing in dollars. There is our dollar sign. On the next slide, we will take a look at the cents. Cents. And 60 cents. Any word with the root cent has to do with 100. Centipede, 100 legs. Centimeter, 100th part of a meter. This time, 100th part of a dollar. Right. So your cent is 100th part of a dollar. 60 cents mean 60 hundredths. As usual, the place value to the left is always 10 times greater. So 60 hundredths are therefore 6 tenths. There is no additional hundredth. So we have what? 60 cents. So we have what? 60 hundredths. So what does 60 hundredths mean? It means that we are in the hundredths region. When it goes to 60, it means that we have 60 means 6 tens, correct?
Yes.
And 10 hundredths are equal to tenths. So the 60 hundredths will be 6 tenths. And we have no additional hundredth, so 0 will take its place right there. Option B is correct, as Jerry stated before. Option B is correct. When presenting cents two places of decimal are always used to ensure that the hundredths place value is present when you are dealing with cents. And when we are programming, there was a computer program by the name of COBOL, Common Business Oriented Language. And in that Common Business Oriented Language, we really made use of dollars because it is business oriented. And we therefore always ensure that we have two decimal places when we are dealing with currency because of the hundredths of a dollar represented by the cents. What is another way of writing 862? Of course, 800 is just 800. That's right, Jerry?
Yes.
What about 60? T has to do with what did I say? T. The
Tens.
right. So the 60 has to do with tens. So it is going to be 6 tens. That's right?
Yes.
And 2. And the 2 will represent 2 what?
One.
2?
One.
Okay, 2 ones. Let us first write the number down with the place values of the digits. The smallest place value will be to the right, and place values increase to the left. So the smallest place values will be to the right, and the place value will increase to the left. So there we have that. Ones, then tens, then hundreds. Ones, tens, hundreds. We have 2 ones. If we separate the ones digit from the rest of the number, a place holding 0 will have to occupy its place in order that the remaining portion of the number retain its initial value. So let us take out the 2 and put it somewhere there. 2 what? 2 ones. Notice that the 2 ones are still in the ones column. That's right?
Yes.
Okay. Suppose we did not put a 0 here, or when we separated the 2, there was no 0 here. Would that be correct?
Yes.
If we did not have any place holding 0?
No, it wouldn't be correct.
Why wouldn't it be correct? The answer or the number that remains would be what?
86.
86, right. And we know that it cannot be 86 because we had 862 to begin with. So we know that it is 860. We will also separate the 6 tens, leaving behind the place holding zeros that preserve the place value of the 8. So take the 60 there. Is it correct to have these place holding zeros? Is it correct to have these place holding zeros?
Yes.
Yes, it's correct to have these place holding zeros. If we did not have the place holding zeros, then the result would be only
8.
right. And it cannot be 8, so we have to ensure that those place holding zeros are there. The number is therefore 800 plus 60 plus 2, and it is represented by option
C.
It is represented by option C. Let us write the number again and include the place values. So let us go again. Include the place values. Also, separate the digits as before, leaving place holding zeros to maintain the place values of the digits. Just like we had before. The numbers that we have there may only equate to 862 if we add them. Okay?
Yes.
So let us add them. What is the result there, Jerry?
2.
And what is the result of the next column?
6.
Right, because all we are doing is just adding with those. And what is the result of the next column?
8.
Right. There is nothing to be added to the 8, so it returns as it is. That is why on the previous slide, after separating the digits according to their place values, we concluded that they must be added in order to give the original number. Is that right?
Yes.
As a matter of fact, we must understand that every number is the sum of the values of the digits that it contains. Right? And that is what the problem is there to enforce or to reinforce. It is there to reinforce that when we have a particular number like 862, 862 is what? The sum of 8 hundreds, 6 tens, and 2 ones. And all of those have to be added together in order to give 862. Which of these diagrams shows a quarter shaded? Which of these diagrams shows a quarter shaded? We can easily tell which shows a quarter shaded if we know what a quarter means. What do we mean when we say a quarter? What is a quarter? That quarter, of course, is a fraction. Which one has a quarter shaded? The denominator of the fraction tells us the number of equal parts that the whole is divided into. Okay? So the denominator of the fraction tells us the number of equal parts that the whole is divided into. So Jerry, what will be the denominator of the fractions for what we have there?
4.
4. So we have 4 equal parts. Each one is divided into how many equal parts?
4.
4 equal parts. Each one is divided into 4 equal parts. Each whole is divided into 4 equal parts. The denominator is therefore equal to 4. 1. The numerator tells us the number of equal parts that are involved. On this occasion, the number of shaded parts. On this occasion, the number of shaded parts. So the numerator is 1, and that will tell us the number of parts that we are talking about. And in this particular case, the number of shaded parts. The numerator is
1.
How many parts must be shaded?
1.
In which of the options is 1 shaded?
Option C.
In which, I'm not saying in which of the option is 1 not shaded. I'm saying in which of the option is 1 shaded.
Option B.
Right, option B. The numerator is 1. Which option has only 1 part shaded? Option B has only 1 part shaded. It is the correct answer. On the line segment, which number is at the point shown with the arrow? On the line segment, which number is at the point shown with the arrow? There is your arrow shown on the line And we need to know which number is at that point. The arrow is pointing on the mark that is halfway between 1 and 2. The number that comes midway between 1 and 2 is 1.5. The correct answer is option C. There it is. If we count with the number that we have there, we will realize that we are normally just counting by 1. So if we count by those numbers that we have right there, we are normally just counting by 1. We are counting by 1. If numbers are placed at the blank marks in order that we do not skip out any of the marks, we will not be going up by 1 each time, but by half each time. So we will not be going up by 1 each time, we will be going up by a half each time. 0, then a half, then 1, then 1.5, then 2, 2.5, 3, then 3.5, 4. But initially, the numbers that we had there going up by 1 each time. But if we include the intermediate values, we'll be going up by a half each time. And take note that the arrow that we have there is pointing on one of those intermediate values, 1.5. Here we see again that the arrow will actually point on 1.5, verifying that option C is correct. We will continue with problem number 19. When you count in hundredths, which number comes next after 3? When counting by hundredths or in hundredths, which number comes next after 3? When counting in hundredths, the digit in the hundredths position will increase by 1 each time. When it reaches 10, the tenths digit will increase by 1 and the hundredths digit will start again from 0. We are increasing our hundredths digit by 1 each time, and as soon as it reaches 9, if one more is added, it goes to 0, that is the hundredth digit, and 1 is added to the tenth digit. This is because the digit to the left is always 10 times the current place value. In this particular case, the tenth digit is 10 times the hundredth digit. So as soon as the hundredth digit gets to 10, the tenth digit will increase by 1 and the hundredth digit will return to 0. The number that we are focusing on is 3. When we are counting in hundredths, which number will come after or next after 3? Which means the very next one. There is the number in the statement of the problem. Increase the hundredth digit by 1 because we are counting in hundredths. Increase the hundredth digit by 1. That's all. The correct answer is therefore option
A.
with the understanding that when counting in hundredths, the digit in the hundredths position will increase by 1 each time. We may just add 1 to the hundredths digit in 3. So that is 3, the number in the statement of the problem. We may just add 1 to the hundredths digit. And what do we know? 0 plus 1 is equal to
1.
With nothing to be added to the other digits, they will return as they are. The decimal point will also be vertically aligned with the 1 in the original number. So there we have it. The correct answer is therefore option
A.
That is really a crude way to add 1 to the hundredths digit and may only be suitable for rough work. On the next slide, we will take a look at the appropriate way to do it. So we will show on the next slide the appropriate way to increase the hundredths digit by 1. The one that will be added to the hundredths digit should be shown to be 1/100th. The decimal point with the other place holding zeros must therefore be included. If we want to do it the correct way, we have to include the necessary place holding zeros. We need to also include the decimal point, and we need to have our proper addition form or addition format. And we will just add as normal. 0 plus 1 is equal to 1, and 0 plus 0, that's equal to 0. Vertically align the decimal points with the others. So we have done that, and then we will add the 3 also. The correct answer is option A. When counting in hundredths and we get to 10, 1 is added to the 10th digit, and the hundredths digit returns to 0. On the next slide, we will take a look at why this is so. Remember that when, let us say that the hundredths digit is at 9. When we increase it by 1, what will happen? It will go to 10 hundredths. And 10 hundredths will make 1/10, because the place value to the left is always 10 times the present place value. And by so doing, the hundredths digit will return to 0. So we will count as usual in hundredths, and it will be done by continually adding 1 to the hundredths digit. Right there. Let us continue to count. We need to add 1 to the hundredths digit because we are counting in hundredths. So if we continue to count, we need to just add another 1 to the hundredths digit. On this occasion, we will do regular addition rather than just flipping digits. So we will just make sure that we do regular addition. What happens? 1 plus 9 is equal to
10.
And we do what?
Put down the 0 and carry the 1.
0 will go right there, and the 1 will be carried. And then we have 1 plus 2 plus 0, and that's equal to 3. So when we get to 9 hundredths, if we continue counting, the hundredth digit will go to 0 and 1 will be added to the 10th digit. And that is why when we had it earlier on, like that, take note of what happens. As soon as we get to 9, if one more is added, it goes to increase the 10th digit, and the 100th digit returns to 0. When we are counting in hundredths and we are at 9 hundredths, continuing to count will cause 1 to be added to the hundredths place value position. So 9 plus 1 is equal to 10. For 10 hundredths, 0 is placed in the hundredths position and 1 is carried to the 10th position. If 12 oranges were shared equally among 3 friends, which expression will give the number of oranges each friend got?
Option B.
Option B, 12 divided by 3. Let's see what we make of it. We are sure that 12 divided by 3 is correct, but we need to pay attention to some special words, and we also need to apply principles strictly. Shared and each. 12 oranges were shared, but shared is not so important as equally. So equally among 3 friends, which expression will give the number of oranges each friend got? Whenever we see the word per, share, or each in a mathematics problem, it is usually a clue that we need to divide. But this is when we want to find the amount of each. So when we are finding the amount of each, what do?
Multiply. Divide.
We divide. When we want to find the amount of each, we divide. In this case, we are actually finding the amount of each. As a matter of fact, the overall amount or total, which is 12, is already given. So we are sure that this is not a multiplication problem. Why? Because if we are multiplying, we would be finding the total amount. Is the total amount given, Jerry?
Yes.
What is the total amount?
12.
Right. So we are sure that we need to find the amount or the number of each, and that will be done by
Division.
Division will therefore give us the correct answer. The correct answer is option
B.
Each does not always mean that we should divide. If we were given the number of each and we need to find the total amount or the total number, then multiplication would have been correct. When we see each, it does not mean necessarily that we need to divide. We divide when we are finding the amount or number of each. But when we have the amount or number of each and we need to find the total number, then we need to multiply. It is not practical to add or subtract oranges and friends. Those two operations are illogical and therefore incorrect. So we are talking about 3 friends and 12 oranges. We cannot add or subtract oranges and friends. Therefore, the options that contain addition and subtraction, those are illogically incorrect. We may physically demonstrate that division is appropriate by physically sharing 12 oranges. How? Equally. And division is only suitable for when we are sharing how?
Equally.
We may physically demonstrate that division is appropriate by physically sharing the oranges equally. How many oranges, Jerry?
12.
Right. And I am purposefully putting the oranges down and not using 3 or 4 in any row. So I'm using 5 by 5. So we are more obviously solving the problem if we use 5 in each row until the number of oranges are exhausted. So we have, how many slots do we have there?
12.
Right, we have 12 slots there. And if we cover each slot, then how many oranges we must have?
12.
Okay. So there are our oranges. Very ripe, very yummy, very delicious, very succulent. Shared equally. There is a bit of detail that makes the problem suitable for division. The inclusion of the word equally tells us that the oranges are not only shared, but each one gets the same number of oranges. That is, each one of the friends gets the same number of oranges. If each one did not get the same number of oranges, then division would not have been appropriate. So when we are dividing with the understanding that the shares are
equal.
Right, the shares are equal. On the next slide, we will represent the 3 friends and ensure that they get equal number of oranges. Let us first give representations of the how many friends?
3.
3 friends. There we have the 3 friends. Shared equally. If we share them equally, then we will begin by giving each friend an orange. That means each friend must get an orange to begin with. Is that right?
Yes.
Okay. After that is done, what should we do, Jerry?
Give each friend another orange.
Okay, give each friend another orange because we have to do it what?
Equally.
Right. And after that is done, what do we do, Jerry?
Give each friend another orange.
Okay, give each friend another because we have to make sure that we do not give one 3 and then give the other 1. But when we are giving, we give each friend an orange round about the same time. So there we go. Oranges shared. Each of the friends got how many oranges do we see there?
4.
4 oranges. Considering that we had 12 oranges and they were shared equally among 3 friends, what operation would give an answer of 4? Considering that we have 12 oranges shared equally among 3 friends, and each friend got 4, which operation would give us an answer of 4?
Option B.
Which is?
12 divided by 3.
Right. Division will actually do that for us. So we are sure that division is the right one. Share is synonymous with division, especially when we are finding the size of each share. The size of each share is 4, which is the result of dividing 12 by 3. So if we take 12 and we divide 12 by 3, what will be the result? When dividing by 3, knowing our 3 times table simplifies the process. If we are dividing by 3, we need to know our
3 times table.
Right. 3 ones, 3. 3 twos, 6. 3 threes, 9. 3 fours, 12. 3 fours, 12. By our multiplication table, 3 fours equal 12. It therefore means that 3 will go into 12 how many times?
4 times.
4 times. We have confirmed that division is the correct option. How did we confirm it? We actually do the sharing of the physical oranges, and the result was that each student or each friend got how many oranges?
4.
Then we proceeded to divide 12 by 3, and what did we get?
4.
So that proves it, that division is actually the correct one. When solving a problem with words like share and each, if the size of each is required, we divide, right? But if we have the size of each and we need the total, then we
Multiply. Multiply.
That's correct. Which fraction of this set of shapes is circles? What fraction of the sets of shapes is circles? What fraction is circles?
2/8.
I heard Jerry shouting already, 2/8. How do we know that it is 2/8, Jerry?
Because there are only 2 circles there.
There are only 2 circles.
And 4 square rectangles or squares, and 1 triangle.
Right, 2/8. So let us go straight ahead. How do we know what fraction is circles? We do not forget our fraction. And how do we label our fraction? We have the fraction bar, we have the numerator, and we have the denominator. The denominator in this particular case, Jerry, is what?
8.
How do we know that the denominator is 8?
Because you have 8. You have 2 circles. What?
Because we have what?
8 shapes.
Right, we have 8 shapes in all. The total number of shapes is 8. So the total number of items from which to choose will be the denominator of the fraction. And we have there how many of them? We have 8 shapes. So the denominator will therefore be 8. The total number of shapes is?
8.
The denominator is therefore?
8.
The numerator tells us the number of shapes spoken about. On this occasion, the number of circles. So we are required to tell what fraction of this set of shapes is circles. And the number of circles, as a matter of fact, the circles are the shapes that are spoken about. And that will be our numerator. How many circles do we have there, Jerry?
2.
We only have 2. There we have them. 2 circles. There are 2 circles. The numerator is equal to?
2.
Right, so the numerator is equal to 2 for those 2 circles. The fraction that we have is represented by option B, which is 2/8. Martin was the 5th person to cross the line in a race. Tony came 2 places in front of him. What was Tony's position in the race? Martin was the 5th person to cross the line in a race. Tony came 2 places in front of him. What was Tony's position in the race?
3rd.
And Jerry is saying that it is 3rd, and Jerry is correct. There we have them crossing the finish line in the race. Let us count the boys in the order in which they cross the finish line. Can you remember which one crossed the finish line first, Jerry? Which one crossed? Red. And then which one crossed next? And then which one after that?
Yellow.
And so on. So 1, 2, 3, 4, 5. Those are the numbers which suggest the order in which they cross the finish line. The order may be given in ordinal numbers as follows. Ordinal numbers. Position 1 is called
First.
Position 2 is called
Second.
Position 3 is called
Third.
Position 4 is called
Fourth. Third. Fourth. And fifth.
and then
Fifth.
fifth. Right. Position 5 is called fifth. Position 4 is called fourth. Position 3 is called third. Numbers like first, second, third, fourth, and fifth, and so on, are called ordinal numbers. They are called
Ordinal numbers.
They are called ordinal numbers. Why are they called ordinal numbers? Because they tell the order in which events occur. They are called ordinal number because they tell us the order in which events occur. So there we have all of the boys that we proposed would have finished the race, and we have their ordinal numbers. Smallest ordinal number is at the front, and the largest ordinal number is at the
Back.
right. So position 1 is at the front, and the last position, or the fifth one in this particular case, will be at the
Back.
back. Martin was the fifth person to cross the line in a race. Which one is Martin?
Blue.
Right, Martin is the blue one because Martin is actually the fifth person to cross the line, and the one in blue is the fifth person. Tony is 2 places in front of Martin, and Jerry is saying that Tony finished third. Since Tony finished in front of Martin, his position is closer to the front of the race than Martin's position. So his position is
Third.
third. Tony finished in front of Martin, therefore his position is closer to the front of the race. From where Martin is, step 2 places towards the front or forward. 1, 2. And if we go 2 places, we will go 2 places from Martin, and those 2 places will take us to which one?
Yellow.
Right, to the yellow one. Therefore, the yellow one has to be
Tony's.
right. So the yellow one belongs to Tony. And Tony finished in third position, as Jerry would have figured out a long time ago. The front of the race is associated with the smallest ordinal number and the highest position. The lowest position belongs to the largest ordinal number. It is at the back of the race. What is the most whole number of 6 in this set of shapes? What is the most whole groups of 6 in this set of shapes?
2.
And Jerry is saying that it is 2 already. What did you say, Jerry?
2.
Okay. Anyway, that we will solve this problem, counting the shapes will simplify our method. It is good if we know how many of them, right?
Yes.
And even if we are not taking or counting all of them at once, we still need to count. So we count, and we have how many of them in all?
15.
There are 15 of them. Dividing by 6 is one way that we can find the number of whole groups of 6. So we will take 15 and we will divide 15 by 6. 6 into 15, Jerry.
2 times.
Think of our 6 times table when dividing by 6. You have to take a good look before it goes away. Not Jerry, because Jerry knows his multiplication table. And not only that he knows them, he is very sharp on his multiplication tables. So if there is anybody else looking, look very quickly because it will be gone in a few seconds. So 6 into 15 will go how many times?
2.
We say 6 into 1. We can't. Then say 6 into 15 goes
2 times.
2 times. 6 times 2 is equal to?
12.
And 6 threes are?
18.
It means that 6 will go into 15 2 times because 15 is greater than 12. But it is less than 18. 15 is less than 18. Therefore, 6 will not go into 15 all of 3 times because 6 threes are 18. But it will go into 15 as many times as 2 because 15 is greater than 12. So we will get 2 sixes out of 15. So it cannot go as many as 3 times into 15. It means that there will be a remainder of 15 minus 2. 15 minus 12, which is 3. But the problem said nothing about a remainder. The answer is therefore option
A. B.
The correct answer is therefore option B. Groups of 6. Pay attention to groups of 6. Since we need the number of groups of 6, we may group them in sets of 6. We may group them in sets of 6. So we will count off 6 and we tie them up like that. And what do we do again, Jerry?
Put another box. Count off 6 more and put them in a box.
Right. Jerry says that we should count off 6 more and put them in another box. Which is right. How many boxes do we have?
2.
How many groups of 6 do we have? We have 2 groups of 6. There are 2 groups of 6 and there are also 3 leftovers. The statement of the problem asked for the number of whole groups of 6 and said nothing about the remainder. There are only 2 of them. Only 2 whole groups of 6. We have the red one and the green one. Only 2 of them. The correct answer is therefore option B. Mary was asked to write the number 732 and 8/10. She wrote her number on the table below. What should she change to be correct? Jerry, there's something blatantly wrong with the way that it was written right there. Blatantly wrong with the way that it is written right there. What is it that is so wrong? It is obviously wrong, Jerry. What is it that is so wrong? What is it that is so wrong?
2 digits.
2 digits where?
At the 10th.
Right, 2 digits at the 10th position. That's right. So we are sure that that is our incorrect format that we need to change. So even without dissecting the problem, even without working it out, we are at our answer already. We cannot have 2 digits in one place value. Can we have 2 digits at one place value? No. So Put 8 instead of 80 in the tens column. Option C is therefore correct. Let us not focus on the wrong, but pay special attention to the right and use it to find a solution to the problem that we have there. So we are going to solve the problem just in case the problem was more sophisticated. We know the answer already, but let us solve the problem taking a correct approach. So let us not focus on the wrong, but pay special attention to the right and use it to find a solution to the problem. The number has 7 hundreds, 3 tens, and 2 ones. 7 hundreds, 3 tens, and 2 ones. 700, 3 tens, and 2 ones. 30 means 3 tens. So we put those in. The digits that comes after the decimal point are easy to figure out. Additionally, on this occasion, there is only one of them, so just one single digit should go there. And that is the 8. 8 tenths. Everything would be a perfect match if instead of 80 in the tens place, there was a single digit, which is 8. So it would be perfect. Everything else is the same, except that 80 in the 10th position. So we need to replace that what? 80 in the 10th position with the correct thing, which is just to have 8 in that 10th position. The correct answer is therefore option